Well, okay, so we're starting our next talk this afternoon. Sorry, we're running a bit late. The first talk, I would blame the first talk for running a bit late. So, um, the speaker for our next talk is Professor Yuehua Cui. So, Yuehua, he's a professor and graduate director of the Department of Statistics and Probability of Michigan State University, and his research interests are statistical genetics, statistical genomics, and longitudinal data analysis. I hope I got it correct. Functional data analysis, mixture model, and statistical applications in biological sciences. And he has also served as editors of many journals in this area. So the talk today is from association to causation, and I'll leave the stage to you. Okay,
All
let's
right.
welcome the speaker.
Okay, thank you very much for coming to this session. And also, I would like to thank the organizing committee to invite me to give this talk. And this is really a great honor and a great pleasure to be here. And this is my first time to visit this place, and been really enjoying the visiting so far. And I took a tour of this campus, this beautiful campus with mountains. I grew up in the mountains area, so I really enjoy the mountains. So I live in Michigan. Michigan is really flat. So we have a little hill. It's about 100 meters high. We call it mountain. We call that mountain. So it's a really little hill. All right. So today I want to share some of our work on causal inference with the Mendelian randomization. And this is joint work with student Ruxin Shi. So Ruxin is currently fourth year PhD student, and Jialin is graduate 2 years ago, and now is Moderna. You know the Moderna with the vaccine, and also Stephen Burgess. All right, so I want to start with an example. So this is the research published many years ago, back to the 90s. And so they wanted to evaluate the vitamin E supplement use and the relationship with the risk of coronary heart disease, CHD. And the two of the studies shows, and taking the vitamin E supplement can reduce the risk of CHD. So you can see this is relative risk and lower than 1. And there's another study with RCT that's randomized the controlled trials, and it shows this taking vitamin E supplement has no really effect on reducing the risk of CHD. So what's going on? And these are the observations based on some of the follow-up. And I think this is this one is actually a longitudinal study over 10 years period, and it shows reduce the risk. But based on the RCT, there is no effect for vitamin E on CHD. And we know the RCT, and that's the golden standard for causal inference. So if you wanted to establish causality, and the golden standard is to perform RCT, randomized controlled trials. By doing the randomization, you actually control a lot of the confounding factors. At the end of the study, then you can compare different groups, control group, treatment group, then you can establish a causality. So there are many other examples. For example, vitamin C, vitamin A, and many other supplements. And so what's the explanation? So why the study shows there is a effect by taking those supplements, reduce some of the disease, but actually by doing the RCT, there's no effect. So it turns out that there is a lot of the confounding risk factors. And if you're not controlling those risk factors, the relationship and you establish that's not really causal. So the confounding factors, including alcohol intake. So there are many some of those measurable, observable. You can measure, you can observe those confounding factors. But a lot of times those confounding factors, you don't even know how to measure. So there's no way you can measure those confounding factors. So those exercise, you can measure it, smoking, and alcohol intake, and so you can measure those, but some of those are unobservable or unmeasurable. So the limitation to observational studies is confounding. Okay, So our interest is in establishing the relationship between the exposure and the outcome. And for example, vitamin E and heart disease, say if you're taking vitamin E, has a causal impact on the heart, reduce the risk of heart disease. But if you're not controlling the confounders, so confounders could affect the people, the way they're taking the vitamin E, and also affect the heart disease. And these confounders can distort the relationship between the exposure and outcome. So the correlation does not imply causation. We all know that, right? So even though you have a strong correlation, but does not really imply causation. So the only way when you establish causation is you have to control those confounding factors. So when the confounding factors, those are observable, you can include those confounding factors. If you do the regression analysis, you can put those confounding factors as a covariates, right? You can adjust the effect of confounding factors. But if you don't observe those confounding factors, and then we need to use some other tools to do the causal inference. So as I mentioned, the RCT is a gold standard for inferring causality, and for RCT, randomization is the key. So you randomize it, and you have a control group, you have an exposure group. So you do the exposure group, you do the intervention, and there's no intervention. And then at the end of the day, those two groups, you compare the difference of those two groups, either mean or some other, the ratio or some other measurement. But there's still a need for the observational data. So the RCT is not always ethical or practically feasible, and it can be something toxic. And also it can be very expensive, and so there is still a need for observation. A lot of the time we collect data; those are observational data. So these are not really randomized data. You go to the hospital, you collect the data, you take the measurement, and those are observational. Those are not really randomized. Okay, those are not randomized. So when confounder is observable, you can do a lot of things to do the causal inference. You can do the matching, stratification, and do weighting. And a lot of time people use a propensity score. Okay, you do the propensity score. Propensity score is a probability measure. So the probability of somebody given the treatment and given the covariates, baseline covariates, you can calculate that propensity score and use the propensity score to do the matching, or stratification, do the stratified analysis, you do the weighting, inverse the weighting to do the causal inference. I'm not going to talk about those, and these are to the potential outcome framework. There's a lot of work done for causal inference in that direction. So all these assumptions is there's no unmeasured confounders. So what if you have unmeasured confounders? So all the confounders are unobservable. So one of the tools people use is the instrument variable regression. So IV regression. So IV regression has been studied for a long time in econometrics. Okay, so this is quite popular tools in econometrics. People trying to study if you have government has certain policy, see if that policy has any causal consequence on some of the events. So what is the IV regression? So there are three assumptions for to find the IV variables. So this is the diagram shows. So we're interested in exposure relationship between exposure X and outcome Y, and because the confounders affect the X and Y, so the correlation between the X and the Y is distorted. Okay, so we need to find something, and instrument Z. So what is the instrument Z? So there are three assumptions you need to meet to make the Z as a valid instrument. So the first one is Z has to be associated with exposure X. So Z affects Y only through X. Only through X. So if Z can affect, so there's another model. So this the causal diagram is very similar to the mediation analysis. So the mediation analysis is Z affect Y through X as a mediator, and also Z can have a direct effect on the outcome Y. So in that case, that's a mediation model. And in this causal model, Z can affect Y only through X, cannot through other pathways or other ways to affect Y. So actually that If Z affect Y, direct affect Y, then those are not valid IVs. They're not valid IVs. So the second assumption is that Z has to be independent of confounders. But this assumption is more, it's untestable. A lot of times it's untestable. You cannot really test whether Z is independent of confounders. Why? Because a lot of times confounders, you don't even measure those confounders, right? So there's more, you assume this satisfy that assumption, and another one, third one is Z cannot have a direct effect on Y. All right, so that's to make Z as a valid instrument. And then this is a very popular linear structure model, two-stage linear structure model. And the first stage you do, this is called the two-stage least square estimate. And the first stage you do this regression, and you get the gamma hat, and then you plug in and get an X hat. And the second stage, and you get the, oops. And the second stage, you use X hat, plug in the X hat, and do the regression, you get an estimated beta, and the beta is the causal effect. And Y, and you can see this X hat is a PZY, PZX, so PZ is the orthogonal projection matrix. So we know the Z is independent. Z is independent of the confounders, is really independent of U and the V, both U and the V. And the reason the confounders affect X and Y is if you look at the model, is U and the V, they're not independent. U and the V, they're not independent. So the correlation, derivative correlation of U and the V indicate the strength of the confounding, okay? But Z is independent of U and the V. Now the X, and the X hat is a projection on Z, and Z is independent of U, then the X hat is independent of U, and then you can use that projected X to do the regression, you get a beta, and that's the causal effect, okay? But the challenge is IV not always available or not easy to find in real applications. So in MR analysis, in Mendelian randomization analysis, people use SNPs as IV to infer causality, okay? So there are many applications of the MR analysis in many areas, and in particular in recent years, and you can see that there are tons of publications regarding the application of MR analysis. And I got a review invitation almost every week, or even sometimes twice a week. And there is abuse of MR analysis. And so I will mention that briefly in the end of the talk. So why that's an issue. So MR relies on Mendel's law of inheritance. So there's segregation and independent assortment. And so this is the side-by-side comparison of MR and RCT. And so the RCT do the randomization. And for MR, you have the random segregation of the two alleles. So we have two alleles. And then you have an exposure group, you do the intervention. Here you have an exposed group is the functional alleles, and the control groups is the control alleles, the null alleles. Then you still have two groups, and this side is two groups. And because this is the independent assortment and the segregation, and that mimic this randomization process. And here's the example. For example, you have an exposure group is smokers, control groups non-smokers. And here you have the exposure group is heavy smokers with this AA genotype. And then the control group is more like a light non-smokers is the other genotype. So you have two groups, functional groups, non-functional groups, or null alleles. And then you have two groups and which mimic the RCT design. So the common MR approach, there are two main frameworks. One is based on individual level data. We call the one sample MR analysis. And so the process is flexible to model linear, nonlinear effect. So based on individual level data, you have many samples. And now with the UK bank data, you can have more than 500,000 samples. So sample size is not really an issue. And you have flexibility to model the linear relationship or nonlinear causal relationship. And the cons are needing individual level data, which is not always accessible. You have to apply because of DNA, and you need to apply to access those data. And there is some the issues with that with the IV selection bias. which we call the winner's curse, because you only have one sample. Okay. And there's another one, is weak IV bias. So this, with the GWAS data, a lot of SNPs, their effect size is really weak, and that leading to the weak IV bias. Okay, and we propose this MR split to address these two issues. So I will show you what is the MR split. And the other framework is based on GWAS summary statistic. And this is based on two sample MR analysis. So you have two GWAS. Okay, one GWAS is a SNP and the exposure GWAS. You get a beta hat X regression with Z, which are the SNPs. And another one GWAS is a SNP and an outcome GWAS, which is Y versus SNPs. So you have these two. Then you can get the ratio estimator. So beta YZ over beta hat XZ. So for a given Z SNP, you get a ratio, which is the causal effect. If you have many Z's, then you can just combine those with the inverse variance weighted approach to get those, aggregate those individual SNP effect and get a total causal effect. So the pros are easy to access the data. So these are summary statistics are publicly available. So you can download it anywhere. And a lot of those in the GWAS study, they made those summary statistics available online so that people can access those. But the cons is inflexible to incorporate different models and difficult to do sensitivity analysis because you don't have individual level data. And also for the GWAS, these are marginal regression. So you do the regression of the outcome with each SNP one at a time, okay? And when you have the LD correlation of the SNPs, so those are SNP effect, they're not really, they can be affected by LD. And if you use those marginal regression signals and the result, they are not reliable. So that's the limitation for the, but still this the two sample MR analysis is very popular because data is there, so you can access the data. They're a big consortium, and you can download all those data, do the MR analysis. That's why there is abuse of MR analysis currently. People do the two sample MR analysis. Sure. Well, yeah, that's a good question. So with the binary, you can still do this ratio estimator. There is different ways to do the ratio estimator with a binary outcome. So, and people are doing that, still doing that. So, and it depends on what disease you analyze, and yeah. So their approach developed for the binary outcome, but the ratio estimator is not directly do the ratio of these two. So there's a different definition for the ratio estimator with the binary outcome. Yeah. There's another problem. So you cannot really guarantee they're from the same population. Yeah, they can be different population. People are using that, and so there is various issues with if it's you better use the same population. For example, if it's white, and you do the two samples have to be white. So if you use one is white, the other is black, then has issues. Yeah, but there is abuse of the MR analysis. People don't really care. So, so there are review papers, and if you're interested, you can take a look at this. In particular, there is a Nature review method primers, and summarizing the MR approach. So as I mentioned, so what we do is we focus on the one sample MR analysis with individual level data. So even though the two sample is easy to apply, and I'm not comfortable really to rely on those GWAS marginal regression signals. So we work on the one sample MR analysis, and we try to address some of the bias issues with MR analysis. So one is the IV selection bias, or we call it the winner's curse problem. So you have one sample, and you use the same data to select the IVs. And then with that selected IVs, you fit these two-stage least squares, and the same data being used twice, and there is cause the winner's curse problem as an IV selection bias. So the solution is we can do sample split, right? So we have split, we use one sample to select IV, then use another sample to do the effect estimate. But the question is, how do you, once you do the split, sample size reduced by half, that can affect your power, right? So, and we propose an approach, essentially we still use the full data set to do the causal effect estimate. And this is a simulation to illustrate the bias. So without doing a sample split, even the limo, and limo is used for address the weak IV issues. And if you don't do the sample split, you can see that really have the bias. So these effect estimate are biased. And with MR split, so it's not biased. And with a limo, if you do the sample split, it's also not correct to the bias. And the second bias issue is the weak IVs. So weak IVs lead to the weak instrument bias issue. Okay. So there are studies back to the 90s. So these two authors show that when IVs are weak, this two-stage least square estimate is biased and unreliable. And Becker later on shows the two-stage least square estimate is not consistent with many IVs. Even these IVs are valid. So if you have many IVs, even these IVs are valid IVs, if you have many, still this two-stage least square estimate is not consistent. So the solution is we can combine all those IVs to form one IV. This is actually an approach proposed 2 years ago in published PLOS Computational Biology. They form one IV, and the one IV is also called allele score in polygenic risk prediction. This is the same idea. Same idea. So there are two issues. So you have more IVs and leading to larger bias. But the good thing is you have a smaller variance. So in regression analysis, we know this is a bias and the variance trade-off. And if you have a smaller number of IVs and you have a smaller bias, but the issue is you have a larger variance. So when you have a larger variance, even though the bias is small, larger variance, that can affect your testing power, right? So larger variance, testing power. And so we propose this MR split to address both types of bias issues with IV selection bias, with a weak instrument bias. So this is a limo. It's popular approach to address weak instrument bias issues. So I will not go through the details. And this is another one I mentioned with the CFMR. And so the idea is actually our work is motivated by this CFMR work. So CFMR use the coarse fading idea. So take the K equal to 2 as an example. So they split data into two samples, okay, two subsamples. So we call this I1 and I2. So they use I1 to select IVs, then use the data in I2 to form one composite IV as G2 tilde, okay? Then they use I2, data in I2 to select the IV. Then once you select the IV, then you form the allele score in I1, and we denote it as G1 tilde. So then they combine the G1 tilde and the G2 tilde because it's just one dimensional. So they stack together, have a G tilde, and then eventually use X, G tilde, Y. So full data, do the causal inference. But the problem is so this approach, they combine, regardless the IV is strong or weak, they combine all those IV together to form one IV, okay? As I mentioned before, you have less IVs, the bias is small, but you introduce a larger variance. So actually that's actually the case. So I will show you. And this leads to the small bias, but larger variance and low power. And in 2011, there is a paper published in International Journal of Epidemiology. And this work evaluated the different ways for IVs. So this is just single IV, multiple IV. And this is multiple IV to form one composite IV. And it shows actually, so when you have multiple IVs, you form one composite IV, you actually get a smaller bias. And compared to use the multiple IVs. And they also mentioned the other one. So if you have a major IVs, you better separate the major IVs with those weak IVs. So weak IVs combine to form a composite IV, but leave the major IVs as the separate ones. But they just mentioned this idea, but there's no rigorous approach proposed to address this. This is more, they think this is a good way to do it, but there's no approach to develop to solve this. So our work is also motivated by this. So our MR split approach is we randomly split data into two sets, I1 and I2. And with I1, we select P1 major IVs. So there is a definition for major IVs. So we use the partial F statistic to define what is major IVs. And above the threshold, we call this major IVs. Below threshold, we call this weak IVs. For the weak IVs and the I2 data, we combine those weak IVs to form one composite, but leave those major IVs in the I2. So then we do the regression with the major IVs and the composite IV and with the X in the I2 sample and predict the X2 hat. And the same thing in this side, we can use this side to select major weak and then combine the I1, to predict X1 hat. Then we combine this predicted X1, X2 together to form this X hat. And then we do a regression of X hat with Y, use the full data, and then get the estimated beta hat. So our approach is different from CFMR. CFMR is the combined Gs, the IVs, composite IVs, but what we combine is this predict X. So if you want to combine the Gs, because the major number of major IVs in I2, in I1, and the number of major IVs in I2 can be different. So the dimension of the IVs, they're not the same. So you cannot really combine the IVs. But with the combine of the X, predict X, so we kind of address that issue. We can still use the full data to do the causal estimate. I will show you the performance. And this is the comparison with the 2-stage least square and the limo. And you can see the rows, 0.1 is low confounding, and 0.2 is high confounding. And you can see this is the SNP heritability, the effect of the IVs, and the type of error control. And when the confounding is increased, you can see this the 2-stage least square and the limo, they cannot really control the type of error. So it's inflated. And the consequence of that inflation of type of error is you have false positive, right? And then if you compare the power of the MR split with the 2-stage least square and the limo, and it's uncomparable because the false positive is so high. And we also compared the, I don't think I have that slide. So that we calculate the coverage probability. The coverage probability for a 2-stage least square and the limo is, in particular in the 2-stage least square, is really poor and the low heritability. And this is the estimate, comparison of the estimate. You can see these limo and 2-stage least square. If you don't do the sample split, and these are biased, and the MR split is unbiased. And we actually, we evaluated the variance. So we show this MR split, the variance of the MR split is smaller than the CFMR. The different ways to combine and the samples, and our estimate is always smaller than the CFMR. And this simulation study shows, as you can see, this the both approach. CFMR is also unbiased and give an unbiased estimate, MR split, but the variance, different causal effect, the variation of the MR split is smaller than the CFMR. So in different effect size, you can see this is smaller. So that leading to the increased power for MR split compared to CFMR. And the another issue is that when you do sample split, and you have the variation of the sample split, right? So if you do one sample split, and due to randomness, and so ideally you need to do multiple split, right? So we propose you do the multiple split, but the question is how many splits you do. Ideally, the more the better, right? So you can do many splits, but the more splits leading to high computational cost. So if you do multiple splits, and each time you can get an estimated beta hat, and you can get the testing of the p-value for the causal effect, right? And when you do the multiple split, then we combine the p-values, use this Cauchy combination rule to combine the p-values across multiple split and get this aggregated p-values. That's the final p-value for the after the multiple split. And the effect size, we take a simple approach, just take average of the. And this is a simulation, shows the multiple splitting, and this is splitting time, and this is a type-1 error. So we want to see the when, after how many sample splits, you get a stable type-1 error, okay? And the top panel is for low heritability, and the bottom is kind of the high heritability. And this is sample size of 500, 1,000, 2,000. And you can see as the sample size increases, and the number of splits, you don't really need that many splits. You can get a stable type-1 error. So, but when the sample size is small, you need more. Typically, you need maybe 50, 60 sample splits, good enough to. And this is for the power evaluation. And the same thing. So power, when the sample size is small, when you split it 50 times, or you get a stable power, okay? And for the real application, so we apply to this CRIC data. So this is for chronic renal insufficiency study. And the CKD, chronic kidney function is measured by the eGFR and UACR, two measurement. And so low eGFR and high UACR values indicate impaired kidney function. And the goal is to evaluate the relationship between the CKD function and apparent treatment-resistant hypertension. So I'm not sure if you heard about this. So this is apparent treatment-resistant hypertension, or ATRH, is kind of the condition that after you take in 2 or 3 medications of the hypertension medications, you still cannot control the hypertension. So it's become treatment resistant. Okay, so people are interested to find the relationship of the treatment resistant with the CKD function, and is this really CKD function has the causal impact on the treatment resistant for hypertension? Okay. So there is a long debate about the causal relationship between the CKD function and ATRH, and the causal link between them remains unknown. And so treatment resistant is a binary response. It's a binary response. It's either resistant or non-resistant. So we treat this as outcome, and the CKD function, the eGFR and the UACR as exposure, and try to evaluate if there is a causal effect. So this is sample size, number of steps, and we have the GWAS QC and do this linked disequilibrium pruning. So basically, one of the IVs, they're independent, and end up with nearly 500,000 SNPs and over 1,000 samples. So the sample size is not really huge, so it's considered as small. And this is a multiple split p-values out of 50 sample split. You can see it's the majority of the p-values, they're very small. Occasionally you get a large p-value, but after they do the Cauchy combination aggregated p-values, it's quite significant. And this is the after the beta hat estimate out of the 50 sample split, and the average is negative. So we know the higher eGFR indicate the impaired kidney function. So there is a negative relationship, causal relationship between this eGFR and the CKD function measured by eGFR and hypertension, treatment resistant. And for another data, UACR, and this is a multiple split. You can see this is the p-values out of 50 sample split there. Some of those are large p-values, and majority is small. After you aggregate it, you get a significant p-values. And this is the effect estimate. And so again, for this measurement for CKD function, we also establish the causality. All right, so to summarize, we propose this MR split with multiple sample split in one sample MR analysis, and to address the IV selection bias and weak instrument bias issues. And we compared it with other approach. And the simulation, we did an extensive simulation study. And so the manuscript is by archive is currently at the review by the PLOS Genetics. So the first round of review is the minor revision. We submitted, and hopefully I think we'll, by end of this month, we should get a response from PLOS Genetics. So if you're interested in the work, we also have a code in GitHub, so you can try with if you have one sample. And the one thing is, in this work, we haven't considered this pleiotropic effect. So this is the violation of the assumption 3. So if a SNP has a direct effect on the outcome. And the students currently work on this, so we have some nice result to find those invalid. So if you have a SNP has a pleiotropic effect, and how do you find those invalid SNPs? The invalid IVs, they have a pleiotropic effect. And so the simulation study, initial study shows that the result can be substantially improved if you have those IVs that violate that third assumption. So you have a direct effect on the outcome. All right, so I have sometimes I want to show you another study for the longitudinal data. Okay. So their causal inference approach for longitudinal data, you can do the granular causality, you can do some other modeling with the longitudinal data to infer the causality. And so the question is, if there is existence of time-varying confounding effect, so this the confounding effect affects your exposure, affects the outcome, and has a time-varying effect. And in that case, for example, you do the granular causality, you test the two longitudinal sequence, and that sequence, over time, you have a correlation, you show there's a causal effect by granular causality test. But if you have a time-varying confounding, this really, there's a confounder effect of the exposure and the outcome over time, and that kind of the correlation pattern is actually does not reflect the causal effect. Okay, so that's the concern, and we think so. Why don't we use this IV regression for longitudinal data to do this kind of analysis, causal inference? So there is a motivating example. This collaborated with the professor from the MSU psychology department, and they're interested in the causal effect of hormone level and on the emotional eating behavior in teen girls. So usually in teen girls in the teen age, and some experience, they call it binge eating. So binge eating in Chinese is 暴饮暴食. So then the consequences getting, you can imagine if you 暴饮暴食, there is a consequence, right, for that. And so the hypothesis is that may be the hormone level. So the hormone associated with that kind of the phenomenon. And we wanted to establish if there is a causal effect of hormone level on the emotional eating behavior. Okay. So the hormone level, there are two measurements. So we consider as exposure. One is the estrogen, and the other one is the progesterone. Okay, two measurements of hormone. And the emotional eating behavior, they use this questionnaire on the outcome. One is called the DEBQ, and the other one called the PANAS. So these are based on the questionnaire and scores. We all know these questionnaire scores are quite noisy. So, and each individual is measured on 45 consecutive days, and we merge those to 16 time points according to 8 menstrual phases or cycle. And this is the 8. So starting with the ovulatory phase all the way to this is the cycle, the phase 8. This is the cycle. And these are data sample size not great. It's only over 225. And we have for each phase, we take 2 measurements for each phase. So we reduce 45 days to 16 time point. Okay. And this is the hormone level, and this is the mean, and these are the risk outcome, the 2 outcomes. So we propose this time-delayed causal effect model. So the first stage, and this is the second stage, and there is a time-varying effect for the IVs to the exposure hormone, and the alpha T is time-varying coefficient. So we use a non-parametric approach to model this alpha T. You can do the non-parametric B-spline or other non-parametric technique to estimate this alpha. And then we use this QIF, quadratic inference function, and to test this alpha TJ, whether it's significant from 0 or not, to select a G. And for the second stage, and we have this model, we have a P and we have a Q. So what is the P and a Q? So this P and a Q really determine how many time points, exposure time points affect the current outcome, YT, and also the Q determine the lagged effect. So for example, if P equals 1, Q equals 0, this model reduced to this one. So that means current exposure affect current outcome. So if P equals 2, Q equals 0, means the current outcome, current exposure, and the previous exposure, two time points. One is current, one is the previous. So it's one lag and affect the current outcome. So if P equals 1, Q equals 1, that means previous will be xtj minus 1. Previous time exposure affect the current outcome. So the Q will really control if it's Q is 0, starting from the current. If it's Q is 1, you move, there's the previous one time point. The exposure affects the current outcome. And the P is how many time points to affect the current outcome. So this is the model. And how do you determine P and Q? So it's actually, we follow this in the GRSSB approach with a backward deletion technique to select this P and Q. So I will show you the simulation. The actual result is pretty robust to select the optimal P and Q. So in the interest of time, I will not talk about the details of this. And the next, then estimation, the same thing. So this is use a non-parametric estimation. We do the point-wise estimation first. Okay, point-wise estimation. And after the point-wise estimation, we do the smoothed version. Then we smooth those, get a smoothed estimate over the domain of the T. And then after estimation, and are we interested in doing inference? Test beta T equals 0. Okay, beta T equals 0, and this is a global test statistic. And remember, really depends on the R. R really depends on the number of P's. So P is 1 or 2, right? If it's a P is 1, and you only have 1 time point. But if it's a P is 2, then you have 2 sets of vectors, right? 2 sets of vectors for across the T. And this is a test statistic. And so if we can show that this beta, this is smoothed version, smoothed beta RT follows the Gaussian process. Following this, the paper in the Annals Statistics, we can derive the symptotic distribution for Tn. And it turns out that we can show this beta smooth version of the estimate, and it's actually follow Gaussian process. Okay, so with the weight, this is the weight, and this is the mean and the variance covariance. And with that, then we can derive the symptotic distribution for this global statistic Tn, and which is a mixture of chi-square, and this the AM is a mixture of chi-square weighted by the eigenvalues of lambda. And with that, we can use a simulation approximation to really find the p-values for this Tn statistic. And so this is a simulation for time lag selection, and with P equal 1, Q equals 0, and its current exposure affect the current of Y. P equal 1, Q equal 1 means previous exposure affect the current of Y. P equal 1, Q equal 2 is you have time lagged 2 time points. So Tj minus 2 affect Tj outcome, and so on and so forth. And this is the result with P1, Q0. And you can actually accurately select the P and the Qs. So this is a box plot. It's the majority. Occasionally, you select something is not different from P equal 1, different from Q equal 1, but overall, it's really a robust result. But when P equal to 2, so you have 2, in this case, the performance, you might select it just end up with the P equal 1. So it's the performance not as good as when P equal 1. And this is the type-1 error. So overall, different PQs, different sample size, type-1 error calibrated. And for power, and with the sample size small, the power is low, power increase. When P equal 1, the power is good. When you increase the P equal to 2, because the selection of the P's, sometimes you might select it with 1, that might affect the power, especially when the sample size is small. So for example, when P equal 2, Q equals 0, and sample size 200, see the power compared to this one is actually quite not comparable with when P equal 1. But when you increase the sample size to 400, so the power significantly increased. So we applied to this data, and we did many other analysis. I will show you just one result, and this is the, and turns out there is a causal effect between the PRO, progesterone, that hormone, with DBQ. And so we selected the P equal to 2, Q equals 0. That means the current exposure and the previous exposure, the 2 time point exposure, has a causal effect on the current outcome. Okay, so these are the 2 estimates of the beta 1. This is the estimated beta 2 with the confidence band. And these confidence band, these are point-wise confidence band, not simultaneous confidence band. And there's the p-values for DBQ is 0.02. For the PANAS, it's not significant. So this hormone has no causal effect on this PANAS, but for DBQ has a causal effect. And the other EST has no causal effect. EST has no causal effect on these 2 measurements. So only this progesterone has a causal effect on this DBQ2, DBQ measurement. So if you look at this cycle, and so looks like there is a causal effect at the early stage. That's over here, early stage. And the middle for beta 1, so the middle is not really significant because the confidence band cover 0 line, but and significant at the end of the cycle is over here, this stage. And for this one, for the beta 2, the effect, the beta 2 is weaker, much weaker than the beta 1. That makes sense, right? So the current exposure has a stronger effect on the current outcome compared to the previous exposure. And these are over here. You see the significant because confidence band does not cover 0 line, significant over here, and maybe a little bit over here, and at the end of the cycle. So for the beta 2. So stronger effect for beta 1, but not for beta 2. All right. So hopefully with these 2 examples, I convince you the power of MR analysis on the causal inference. And for MR split, we address the IV selection bias and the weak IV bias. And also we propose this longitudinal model for MR analysis. And with the longitudinal MR analysis, we can understand the delayed causal effect. And we have 2 other models with the concurrent model. The other one is the cumulative causal effect model. So I don't have time to show you those. And we can understand this delayed causal effect and with longitudinal data. So the other one I wanted to mention is currently there is a views of MR analysis. So remember the MR analysis is a causal chain. So IV affect outcome only through X. So there is a biological meaning with the IV exposure and outcome. So I searched the literature, and there are some publications, for example, use air pollution as exposure, PM 2.5 as exposure on COVID-19 infection or other disease. But if you think about this IV, so PM 2.5 or air pollution has no genetic basis, right? So your gene, your DNA does not really determine the air pollution, right? Does not determine the air pollution. So this is you can see this abuse of MR analysis. People just download those data and just perform. You can always find some association between the SNP and air pollution, but does not really fit this causal loop. Okay, so that's something. Be cautious when you perform this MR analysis with a causal inference. All right, so with that, I conclude my talk and be happy to take any questions.
Okay, so thanks for the nice talk. Are there any questions from the audience?
Thank you for the wonderful talk. I basically have two basic questions from two parts of your talk. So let's first start with the later part. The data set that you had, that was very interesting, because anyway you could make a cycle in that sense from 45 to you could transform.
Right.
So essentially your causality or the way you did it, that makes sense. But typically when you don't have this type of cyclic structure, you just have the usual longitudinal structure. In my experience, it's very difficult to find out the optimal lag, because the lag effect estimation is not, different methods gives different types of lags, and that can create problems, interpretation. In your case, it makes sense because it's basically the cyclic structure.
Right.
So I was just wondering, like, if I have to generalize this thing for a non-cyclic structure kind of longitudinal data, will that be the same powerful as you were getting?
Yeah, you can still do that. But the problem is, if you started with the time 1, right, for Y, you want to be able to really take any lag.
That's right.
Right, that's true.
That's the problem.
Yeah, that's the problem.
Yeah.
Right, that's a limitation.
Yeah.
But there is no way really you can get away from that. Yeah.
Because every time you don't get this cyclic data, right? Sometimes you don't have
True,
that.
True. So in that case, then it really depends on if you wanted to pick the P equal 1 or P equal 2. If you P equal 1, it's fine. P equal to 2, you can only start with Y2.
That's right.
With the X1, right? So P equal to 3, then that really reduces the number of
the lag.
Right.
Yeah.
The number of the time you can do the modeling with your Ys. Yeah. True.
Okay. And the first part of your talk, again, for the GWAS kind of application, it makes sense because you have a large data. So like 50 split, that's what you said, 50 to 60 to 100 split. That is okay for if you have that kind of high dimensional data. But I think your method is more general. It's not specific to this particular application, right? It's like more general.
Right. Yeah.
So if I have like a small data, say for example, I cannot split really in 50 or 60 different groups. Can I still use the classical methods like data cloning or something, and then can I apply your method?
Yeah. So you're not really splitting to 50 or 60 groups. You still do 2 groups every time. You random. So you have n sample, right? You randomly split it to equal size one time. Then you do another random split. Get another 2 groups. Another 2 groups. Then you repeat this process maybe 50 times. But each time is two groups. 2 groups. 2 subsamples with equal sample size. Right. So then you do the estimation for that 2 groups, and you get the p-value, get the beta estimate, and for that random split. And the second random split, you get a p-value, and get a beta estimate. Third random split, then you do repeat this 50 times, and you aggregate those 50 p-values to get the final p-values. Yeah. So when the sample size is small, and it's actually multiple splitting can improve the robustness. Yeah.
Yeah, I have a question on the second part. I didn't get, where did you use the instrument? The
Genetics,
instrument
SNPs.
for your model. So
G is a SNP.
yeah. Yeah, then when you estimate the causal effect, in the very basic linear model setting, remember you have the ratio, right?
Right.
Where is the ratio here?
So here, if you consider time pointwise, then you can get the pointwise ratio, right? For fixed t. For fixed t, you have this the xt, then you have the beta t, and this is yt. Just for, and that's only works for p equal 1, only one time. For you can do the pointwise ratio. You can do the pointwise ratio. But we're not doing the ratio here. We just, so the first stage you get the xt, you get a predicted, this is just a regular longitudinal variant coefficient model.
And you plug in the second equation.
Right, you get an x hat to plug in here. You plug in here, then the second stage you have to select your p, select your q, and this is the data driven. Based on whatever data tells you what is the optimal p, what is optimal q.
I see.
Yeah.
So you okay. So at a different age, you may have different valid instrument at different t.
Different age.
Different
that's
t. You're gonna have different g maybe, or just single g.
The single g.
It's just a single.
Right.
G.
It's just a single g.
For all the time.
So the g does not change over time.
Yeah.
G does not change over time.
Every time point you have the same g.
Right. Right.
Single
right.
G.
Yeah.
But the longitudinal, is that possible? For example, y can at the t minus 1 can have effect on the x at the t at next time point.
Yeah.
Or,
that's another issue, right? So we didn't really consider that you could have your x affect your y, then
and the time, right?
Right. It's possible. This is a more simplified version of, we did not consider that kind of the effect.
Yeah. I see. Yeah, it's more complicated.
Yeah, it's more complicated. Yeah. Sure.
So just curious about the y. So can you go back to the y? So this is, you said like, so you consider as continuous variable, is that right?
Yeah.
Like,
We consider as a continuous.
Because I figure out the DEQB. I think PNS should be fine, but DEQB is more like a likelihood, like a 1 to 5.
Yeah.
Is that right?
You can see this 1, 2, 3, 4, something like that.
I think usually this in the likelihood, like the typical, right? Questionnaire, right?
Yeah.
Right. So,
We consider as a continuous.
okay.
So just a simplified.
So do you think that also, because I remember you said, yeah, I'm just curious about that, because the model, if it's just like the scale from 1 to 5, right, strictly speaking, I don't know, like a linear model, maybe there's.
Yeah. So we use this one as a kind of we don't have other data to plug into.
So actually my question is, so how difficult if you extend this model other than linear model, or the outcome is not really continuous, like a followed, for example, like the scale type outcome, like 1 to 3 to 5, or more
for the outcome?
Yeah, because here the y you consider is continuous variable.
I think you can do that. So if the y is not really continuous, other scale, for example, binary, it's a little challenging. The challenging part is maybe the lag selection. That might affect the lag selection process. Okay. Yeah. So it's not that trivial to apply this technique for the lag selection. But I think it's still doable, because this approach is basically selection based on, you have to start with an initial value of the P and the Q. So you have started with a large P and the Q, and then gradually you shrink to the smaller P and the Q, and then you for each P and the Q you find this regression sum of squares, and get an F statistic. And they also use the AIC to pick the submodel. You have full model, you have a submodel. And if with other measurement for Y's, I think it's doable. But it's,
you don't think this is going to be impactful on the global test statistics for this?
That's a good question. Yeah, that will have an impact on testing for sure. Yes.
I'm just curious
Yeah,
about this.
yeah.
Because I think it's always challenging when you deal
Yeah,
with
yeah.
outcome is not.
Yeah, that's
continuous.
true. True.
Yeah. Okay.
Yeah.
Thank you.
One more short question, or yes, we have time for one more short question. Well, if not, then let's applaud the speaker again.
Thank you. Yeah.